Thank you everyone for joining once again on another iteration of ML Theory. So today we're very excited to have Tony Silveti Falls talk to us about training neural networks at any scale. So just a bit of a bio about the speaker. So Tony is an associate professor of artificial intelligence at Central Supélec in the Department of Mathematics and a member of the INRIA Opus team. He works at the intersection of stochastic, non-smooth, non-Euclidean optimization theory and machine learning with a focus on developing and analyzing algorithms for large-scale problems. So Tony, I mean, you've oftentimes been an attendee in our community sessions, so it's cool a bit and get you, to present your work. I'm very excited to hear. I must admit it's above my expertise, so I'll let you take the floor and explain the lovely things you've been researching. So take it away.
Sure. Thanks, Andre. So the first thing I'll say is that this is a joint work with many of my collaborators who are all, or almost all, at EPFL in Switzerland. So I think we all agree that training neural networks amounts to solving stochastic optimization problems roughly of this form. And I want to start the talk with a question to motivate things, which is, can we design an optimizer or an optimization algorithm which respects the natural geometry of neural networks? By which I mean in such a way that we guarantee feature learning, so I'll talk more about this in the slides to come, across different model scales. So when I say model, I have in mind deep neural networks with transformer architectures. And when I talk about scaling, I have in mind scaling the width of these layers, which is the modern paradigm for scaling. So let's start by talking about what's been done so far. So if you were to just grab a method off the shelf to solve this problem, you would probably get first SGD, stochastic gradient descent. I think we're all familiar with it. And we can actually write the update of stochastic gradient descent as a minimization problem with respect to a certain Euclidean geometry. And when I say Euclidean geometry, I just mean that we have this Euclidean norm squared in red in the update. So this is pretty vanilla. And there's two conceptual improvements you might reach for right away in the form of adaptivity. So I will divide these into two camps. In the first, we'll have on-the-fly adaptation. These are methods that adapt during the training. So things like AdaGrad, RMSProp, AdamW. And this is really in contrast to what I will call a priori adaptation. So methods that are designed with a problem-specific geometry in mind. So you can think of Bregman methods like mirror descent or no-lips, Riemannian optimization if you have some manifold structure, or maybe also things like maximal update or mu-p parameterizations, which are specific to training neural networks. So I'll go into detail about Adam and mu-p just to set the stage. So if you're not familiar, this is the Adam algorithm. So at each iteration, we're going to draw some stochastic estimate of our gradients. We're going to feed this into a momentum estimator that I show you in teal. And we're also going to keep track of the second moment of the gradients. And you see this in blue. And this second moment of the gradients is going to form a certain matrix that I'll call HK. And this HK can be used to define a certain Mahalanobis norm. And the update for Adam can actually be written as an update like it was for SGD, but now with respect to a Mahalanobis norm. So we've upgraded a bit from the vanilla setting, maybe to like a sherbet, but it's still somewhat plain because the Mahalanobis norm is, after all, induced by an inner product. So in some sense, it's Euclidean. And this doesn't mean that Adam acts like a Euclidean algorithm, because indeed the kernel is changing from iteration to iteration. But I think that we can do better than this. So what are some of the shortcomings of Adam? The first thing is that because it's on the fly, you have to keep track and store those moments that you're going to use to regularize your gradient. And that means that you have to spend some memory to keep track of these. And it's not a big deal when your model's small, but as your model grows to like really huge scales, this starts to matter more and more. It's also unaware of the architecture. So Adam doesn't make any distinction about whether a parameter is in the first layer or the last layer of the model. It doesn't make any distinction about the dimensionality or the matrix structure of our problem. And this manifests itself when we go to look at scaling of Adam. So if I start with, let's say, vanilla atom and the so-called standard parameterization, and I go to train some model and I'm scaling the width of this model, then I'll end up with a plot like you see on the left. So on the x-axis is the learning rate, and we see different colored curves with darker curves corresponding to bigger models. And the takeaway from this is that bigger models actually need smaller learning rates when you use the vanilla atom standard parameterization. And this is not so great because we would like to be able to search, right, for the best learning rate with a cheap small model and then use that to train our huge model where searching is expensive. But we can't do that with the vanilla setup. Another problem when we use optimizers like SGD or Atom is that they fail to learn features as width scales. So what I mean by that is with the standard parameterization, which corresponds to certain initializations of the weights of our network, so things like the LeCun initialization or the Kaiming initialization. And if we use a global learning rate, we can get stuck in the so-called lazy regime. So it's called the lazy regime because the weights move less and less from their initialization as the width goes to infinity. And so we don't really learn features, right? The weights of our intermediary layers are basically frozen at initialization. And when we train a network in this way, as we scale the width, we basically fit these random features. And we're not really taking advantage anymore of like the hierarchical nature of deep learning. So this manifests itself in practice when you actually go to scale things. And I show you that here with this figure from a Greg Yang tensor programs paper. So in the middle, you have the result of some embeddings that were trained using word2vec. So word2vec is like a shallow MLP model where you don't really care about the training loss. You're really just training things so that you can later take the embedding matrix and use this to get some nice embeddings of words into continuous vector space. And if you do this with a finite width model, you get some degree of separation, as you see in the middle plot, between states and cities represented by blue and orange dots. So if you scale things in a bad way, you end up in this lazy or neural tangent kernel or NTK regime that you see on the left, where you've minimized the training loss, but you didn't actually learn any meaningful features that distinguish between states and cities. If we scale things differently, we can hope to have this plot that you see on the right, which is also scaled to infinity, speaking metaphorically, but has much better separation, right, between the states and the cities. So how do we get this plot on the right and ensure that we don't end up with the plot on the left? For that, we can start to look at something called mu-p. So it's a parameterization of your neural network and your optimizer in tandem. And it basically boils down in broad strokes to a certain layer-wise step size scaling and an initialization scaling that takes into account basically the dimensions of the inputs and outputs to each layer. And so if you parameterize things using mu-p, I won't go into the details, but basically you ensure the correct scaling behavior as the width goes to infinity. And so you don't end up in this NTK lazy regime. Instead, you are sure to end up in the feature learning regime. And as a byproduct of this, you actually also have something called hyperparameter transfer. So now the optimal step size for your models of varying width actually all coincide, or roughly coincide, as you see in the figure on the right. And so you can find the best hyperparameter on your cheap to train model, and then use this on your huge, expensive model. And the takeaway from all of this is actually that mu-p is architecture aware, right? It's taking into account the dimensionality of each layer and scaling things in a certain prescribed way. And we can see this really as a form of a priori adaptation, right? It's a way to make Atom aware of the architecture that it's trying to train. And this is really, as we'll see, the right way to go when it comes to things like hyperparameter transfer, even if we're not using Atom.
Sonny, just to interrupt, I believe there was one hand that was up, I think, on the previous slide. So maybe if the participants can just unmute themselves now.
Yeah, if you go back a slide. Yeah, here, I was wondering, since for the NTK and the width 64 and the width infinite, what were the X and Y axis of the graphs here?
Yeah, so the x-axis and y-axis are coming from like PCA of the embedding matrix.
Okay. Yeah, that kind of makes sense. So that's the kind of a grouping that as the width increases, that the blue and the orange kind of groups together at, yeah.
Yeah, we hope that they separate so that we have some distinction between the concepts of state and city.
Cool, thanks.
Yep. Okay, so I want to talk about feature learning in more detail now that I've touched on it kind of ambiguously. So for this, we need a sort of working model of a neural network, and this is what I'm going to use. So without loss of generality, I'm not going to take any bias parameters. I'm just going to have weight matrices. I'm going to assume that our input lives in RP, so it has P components, and that the dimension of all the hidden layers is uniform. It's just equal to M until you get to the final layer where we will output something in R. So I'm going to also assume that the activations are point-wise applied or component-wise applied, and that they are non-expansive and that they map 0 to 0. So you can relax these, but for now, I want to have this just to talk about feature learning, but it's not a restrictive assumption. So with this model of a neural network, we can define what are like the features of the ELF layer just by evaluating the network until the ELF layer. So a partial evaluation will give me the features at the ELF layer. Or you can also think of them as the ELF layer's activations. And I'm going to denote this H to the L, and I'll also denote the change in the features with delta H after one iteration of our training. And so if we want feature learning, or we will define feature learning to be holding if the activations, the features, and the changes to them are stable as we scale the width. So when I say stable, I mean that the RMS norm is neither vanishing nor exploding to plus infinity as the width goes to plus infinity. So that's what's represented by this big theta. It means that it's stable as we scale the width. And if you're not familiar, the RMS norm is just a regularized Euclidean norm that takes into account the dimension. So you divide by the square root of the dimension of your vector space. So to get an idea of how we can ensure this, we can look at what happens for like the first layer to begin with. So the first layer's features, H1, if I look at their RMS norm, just by the definition, I can rewrite this as the first weight matrix applied to the input, followed by the activation function. If it's non-expansive and maps 0 to 0, I can upper bound without the activation function. And then I can upper bound this using the RMS to RMS operator norm. And so if I want my features to be stable, I want that this operator norm is stable as I scale the width. And you can do the same for all the intermediary layers. You get the same result, but for a different operator norm, right? Instead of M to P, now it's M to M or P to M. The same for the last layer. Right? So we really need to control these operator norms, and that leads us to the spectral conditions for feature learning. So these are an alternative to the definition of feature learning that I just gave you, which don't require any assumptions on the activations or the features themselves, but rather assumptions directly on the weight matrices, which are what we actually have access to. So these conditions are going to ensure that these features are stable and that their updates are stable. And we can actually rewrite these with respect to the spectral norm. So I denote with the OP. So the spectral norm is the largest singular value of a matrix. And asking that the RMS to RMS operator norms are stable is equivalent, actually, to asking that the spectral norms have a certain scaling behavior. Okay, based on the dimensions of the input and the output to the layer. And we can extend this to general rectangular matrices just by using the correct scaling. And what we should be taking away from all of this is that if we could control the scaled operator norms layer by layer in the network, then we could feasibly ensure feature learning as we scale width. To be honest, it's really a heuristic because these operator norms are just upper bounds, and we don't know what happens, like if the previous layer's output is in the kernel, then certainly the operator norm bound is not going to be sharp. But it turns out that this is like a super useful heuristic, and it's pretty close to what happens in practice. So this leads us to our general strategy for how we're going to make an architecture-aware optimizer that can train neural networks at any scale. Okay, we're going to cook up some non-Euclidean norms based on layer-wise scaled operator norms. And then we're going to build our optimization algorithm around this norm. And this is what's going to give us a priori adaptation. Right? We're going to encode all the information about the architecture into some norm. And because our algorithm will be using this norm, it will be informed of the architecture. Okay, so that's the background on feature learning and why we're motivated to do this. But now let's talk a little bit about non-Euclidean optimization to have an idea of what we can build on. So we saw already that the updates of SGD can be written with respect to this Euclidean norm. And you might ask, well, what happens if you just change the norm here? If you do that, you get steepest descent with respect to the norm of your choosing. And the nice thing about steepest descent is that the update that you get from doing this actually has a closed form solution using the dual norm of the gradient or of your stochastic gradient estimator. And so as long as you can compute the dual norm and something called the linear minimization oracle, you can always do steepest descent with respect to any norm that you want to pick. Right? So this linear minimization oracle is really what gives us the direction that our update is going to be in. And let's talk a little bit about what this looks like geometrically. So I'm showing you here the linear minimization oracle for several different LP balls. So if you look at the output for the LMO on the L1 ball, you get this vector in red. Okay, if you take the gradient in black and you put it in the LMO, in plain English, it should give you back the least aligned vector that doesn't leave the unit ball. So for the L1 ball, we get this vector in red. And you can also notice that this is a one sparse vector. And this is not by accident, right? This is because the extremal points of the L1 ball are typically one sparse. On the other hand, if we take like the L infinity norm that you see in purple, you actually get a dense vector as your output from the LMO. And this is, again, not an accident because the atoms of the L infinity norm, or the extremal points, are actually dense. So if you pick some norm, you're going to induce some unit ball, and this is going to severely impact what directions you get from the LMO, right? And the directions are not always unique, by the way. So if the set is not smooth, then the directions won't be unique. So some nice things about the LMO is that the output is always on the boundary of the ball. And this means that you have a good idea of what is the norm of the update you're going to make if you use the LMO, because you know the norm of the output of the LMO. And if you know how to compute the LMO for one ball of some radius, then you can actually easily compute it for any radius just by scaling the output. Okay, so for instance, if you have it for the unit ball, you have it for the ball of any non-negative radius. Okay, that shows what the LMO looks like geometrically, but what about analytically? We can actually see the LMO as being the subdifferential of the dual norm. So if we start with some norm, we can find its dual norm, try to think about what the subgradients look like, and that will give us outputs for the LMO. When I say subgradients, I mean in the classical convex analytic sense, nothing exotic like the Clark or anything like this. So if we start with the L2 norm, the dual norm to the L2 norm is actually, again, the L2 norm, so it's self-dual. And the subgradients of the L2 norm, so it's actually differentiable except at 0, and the subgradients are given by G divided by the norm of G, right, times with up to sign. And if we look at steepest descent, then we should multiply this by the dual norm, but the dual norm is, again, just the L2 norm, and so these guys are going to cancel, and the direction that we're going to get is just going to be the gradient or the stochastic gradient. And so if we do steepest descent in the L2 norm, we're going to recover a gradient descent. If we have something non-Euclidean, like the L infinity norm, then what we get is more interesting. So the dual norm in this case is not, again, the L infinity norm. It's actually the L1 norm, because 1 and infinity are conjugate exponents. And so the subgradients of the L1 norm that we can take are sign vectors. If you take a sign vector, this is always a subgradient of the L1 norm. And if we multiply by the L1 norm of the gradient times the sign direction vector, then what we're going to end up with steepest descent is actually a sort of sign descent, or a stochastic sign descent up to this scaling of the step size. And most interesting and most relevant to training neural networks is actually the spectral norm. Okay, so the L2 to L2 operator norm. Now, we can see this guy as the L infinity norm applied to the singular values of our matrix. And in that case, the dual norm is, of course, going to be the L1 norm applied to the singular values of our matrix, which is more commonly called the nuclear norm, which I will denote with this nuke subscript. So just like sign vectors were subgradients of the L1 norm, if we take the analog of this, we have semi-orthogonal matrices, and these are all subgradients of the nuclear norm. So when you go to compute the LMO associated to the spectral norm, you're going to compute the matrix sign, which is really just the vector sign applied to the singular values. So you're going to set all the non-zero singular values equal to 1. And you can actually compute this operation without using the full SVD, either using Newton-Schultz or using randomized linear algebra like sketching. But typically in practice, people are using Newton-Schultz. So if we have the LMO and we have the dual norm, then everything is working. We can do steepest descent. But if we did steepest descent, we'll actually end up multiplying and scaling our direction by this dual norm of the gradient. And this dual norm of the gradient, we don't know how it scales as the width goes to infinity. So we won't be able to ensure that we will satisfy the spectral conditions for feature learning if we just use steepest descent. But instead of using the norm squared, we can replace this by the indicator function for the scaled ball in the norm of our choosing. So if you don't remember the indicator function, it's just a way to enforce constraints. So instead of updating by minimizing this quadratic approximation, we can update our iterates by minimizing a linear approximation to our function, subject to remaining in the ball. So in plain English, it says something like linearize your function, minimize it, but don't go too far, where too far is measured by the norm that you've picked. If we do all of this, then the type of algorithm that we get, where we just directly add the LMO, is going to satisfy the spectral conditions for feature learning, because we're going to ensure that the RMS to RMS operator norm of the updates to our weights is stable with respect to scaling in the dimension. So if you're familiar, by the way, with like conditional gradient algorithms, then the LMO is probably familiar to you as well. So conditional gradient algorithms, or they're also known as Frank-Wolf algorithms, actually are classical. So they come from the 1950s, and they're used for solving smooth, constrained optimization problems. So if we have some constraint set D that's like convex and compact, and we want to minimize some nonlinear function f, at each iteration, we could linearize f, and then minimize this linearization over our constraint set. And this would exactly amount to computing a linear minimization oracle. Instead of directly adding this output to our current iterate, we can instead take a convex combination between the output of the LMO and our current iterate. And in this way, we're taking a convex combination of elements of the constraint set, and we're sure that we're not going to leave it, right? Because the constraint set is compact. And so as long as you have a compact convex constraint set, Frank-Wolf gives you a way to optimize without having to project, just using the linear minimization oracle. And so we're going to use the inspiration from both steepest descent and the conditional gradient algorithm to come up with our contribution. So let's move on to that next. So this is the algorithm that we're actually going to propose to use for training neural networks. And at its core, it's really just like the conditional gradient or Frank-Wolf algorithm. So I'm going to call it the stochastic conditional gradient, or sometimes the unconstrained version, depending on which type of step we take. But the basic idea is that we first sample some gradients using like loss.backward or something. Then we're going to accumulate these by taking the average into some momentum estimator. This momentum estimator is going to get fed into the LMO, which is going to return us some direction that we're going to step in. And then we either step directly in this direction, as was done similar to steepest descent, or we're going to take a convex combination with our current iterate, which is what was done in the conditional gradient algorithm. So if you're not familiar with Frank Wolf, but you are familiar with deep learning, then you'll probably recognize this as just being weight decay. And indeed, that's true. If you just add weight decay, this is another interpretation of what's going on with our two step directions. So in this sense, we can say that the unconstrained version of this algorithm solves an unconstrained problem, while if we do weight decay, we're going to solve something constrained. And this is actually really nice. We finally have the feature learning that's going to be satisfied by taking the LMO direction, and we're actually also going to get an interpretation of weight decay for free on top of this. So if you're familiar with weight decay, there's this big distinction between decoupled and coupled weight decay, which corresponds roughly to seeing it as a Tikhonov regularized problem or not. And a lot of people argue that it should not simply be seen as a Tikhonov regularization because of how this interacts with like adaptive gradient algorithms. And this is also the case in the non-Euclidean setting, right? So this is critical because if you just add weight decay to your unconstrained optimizer, you're going to get stochastic conditional gradient with a radius that depends on the weight decay and the step size. Whereas if you try to use the unconstrained optimizer on the Tikhonov regularized problem, you're going to get this translation inside the LMO. And because it's nonlinear, this is really going to affect the direction that you go into. So we get a new interpretation of weight decay in this context, that it's taking an unconstrained optimizer and turning it into a constrained optimizer with an implicit radius that's dictated by the chosen combination of the step size and the weight decay. Okay, so this is the algorithm that we're going to use. We just need to cook up the norm that we're going to plug into it, and then I'll show you how it works in practice and what we're able to prove for the convergence. So how do we cook up the norm? We first need to think about how to make an LMO that decomposes. So if we're able to assign a norm to each weight matrix in our network, then if we take the max over these norms, the LMO with respect to this new norm is going to be separable. And so when I go to compute the LMO of my gradients or my stochastic gradients, I can do it in a separable way. I don't need to know what happens at layer L to compute the LMO for layer 1, for instance. So this is the type of norm that we'll take. We'll try to put some norm on each layer, and then we'll try to take the max over these guys to get a norm over all the parameters. So if we can specify some norm for the input space and the output spaces of each layer, then this will induce an operator norm that we can use for that layer's weight matrix. And this is coming from the spectral conditions for feature learning. Then we can specify a norm for the whole set of parameters by taking the max. And we know what norms to put on the input and output spaces of the intermediary layers already. Right? So the spectral conditions for feature learning say we should try to control the RMS norm. So if we put the RMS norm on the input and outputs, then what we're going to get is a scaled spectral norm. And so we're going to get for the LMO a scaled matrix sign with a certain scaling that we know, based just on the dimensions of the input and output to the layer. So this works for the intermediary layers, but what about the first and the final layers? Things are not so obvious there. So for the first layer, we have this issue that the input to the first layer can change a lot depending on what application I'm looking at. So if we're looking at images, then the input to the network is probably going to be like a dense vector, right? This is something that's typically not like one-hot encoded. And this is in contrast to language modeling problems where you typically do have a one-hot encoded vector as input to your network. So for image domains, we're typically going to equip the input space with the RMS norm, And this is going to give us a scaled operator norm like we've already seen for the intermediary layers. But for language tasks, the input is one-hot encoded, and this complicates things because actually all LP norms are going to be identical. They're going to be equal to 1 for this one-hot vector. And this means that actually all of the induced operator norms are going to be equivalent. But it doesn't mean that the LMO that you get from these different operator norms are going to be the same. Actually, we're going to get very different ones. So if we pick the 2 to RMS, we're going to get, again, a scaled operator norm, no surprise there. If we pick the 1 to RMS, we're going to get something called the column norm with a column-wise normalization for the LMO. And if we pick the infinity to RMS, we can upper bound this by the 1 to infinity, and this is going to give us a Scion LMO. And using the LMO also informs us how to initialize the network, right? So we want to initialize with a fixed norm given by our choice of norm on the input space. And so we have not only the LMO, but the initialization for all of these guys. And the result of this that we can see on like a toy problem where we're just training a 3-layer GPT on the Shakespeare data set is that we automatically get hyperparameter transfer across width. So I'm showing you the output of training several models using unconstrained Scion with different norms on the input space. So you see it's either sign, spectral, or column norm on the first weight matrix, but all of them give hyperparameter transfer. Typically, the sign is performing the best, or the column norm, and the spectral would be performing much worse if this example wasn't such a small vocabulary size. So this is kind of impacting what we see here. For the output layers, we have no restriction to bound the output in RMS norm if we have some vector output. So we don't need to consider bounding this. Instead, we can consider bounding the maximal entry by taking the L infinity norm. So this would mean that we want to use the RMS to infinity norm on the weight matrix in the last layer. But we could also consider upper bounding this by something that's going to give us the sign for the LMO. And we can see how both of these compare. So I'll summarize this in this table. So if you naively took the RMS on the output, of course, you get back the matrix sign. But if you take the RMS to infinity, then you're going to get this row norm. And if you take 1 to infinity, you're going to get, again, the scaled vector sign. And we tested this on a very small MLP, just trained on CFAR, not to see if it was effective at getting like a good validation accuracy or anything like this, but just to see that it does hyperparameter transfer. And indeed, we find no matter what operator norm you take for the last weight matrix, we still have hyperparameter transfer as long as you take the scalings that we prescribe. So I'll summarize all of this, all of our recommendations. Basically, if you're working with images, you should do spectral on the first layer, spectral for the intermediary layers, and then sign for the output. Whereas if you're working with one-hot encodings, you probably want to use sign or column norm for the first layer. We're going to infer to this instantiation of that non-Euclidean algorithm I showed you when we use operator norms as Scion or unconstrained Scion. And if you want to give Scion a try on your problem, you can try it at this GitHub link where we have the code that's available and, in my opinion, pretty easy to use. What does it look like when you go to actually do this in practice? I want to show you the details with a very simple shallow model. So we have just 3 weight matrices here. We're going to compute our stochastic estimate of the gradient, GK. We're going to feed it into our momentum estimator. And then we're going to compute the update by taking the LMO of this guy. So this is just the definition of the algorithm so far. Then, because we've taken the max norm, the LMO is going to be separable. And so we can compute the LMO on each block corresponding to the different weight matrices separately. If we take, as an example, the sign spectral sign configuration, then the scalings and the LMOs are going to give us this update. So we're taking into account the dimension of the input for the first layer and the dimension of the intermediary layers for the last layer. And just to mention, you can also scale this with layer-wise radii. So this is also something that's possible to do. I see some people confused about this. If we have to pick one norm for the whole network, does it mean we can't have different radii? No, you can definitely have different radii just by scaling the different norms on each layer. So this is what it looks like to do one update of this, let's say mathematically. And there's also a question when it comes to practice about what is the correct scaling convention for the output of the spectral LMO? Because while I have prescribed one thing, you will find different prescriptions in, for instance, the Kimi paper on Muon or in the Muon blog post itself. So if we take some matrix W, which is d out by d in, then the Scion scaling says you should take, based on the spectral conditions for feature learning, the square root of d out over d in. But this is not what you find in many other works, right? So in the Moonlight Kimi paper, which is also looking at spectral LMOs, the scaling is given by the max of the square roots. And this is actually not leading to hyperparameter transfer. And this is something that they commented on in the Kimi paper, that it's an open question, what will give hyperparameter transfer for Muon? So I think that Scion gives a great answer in this direction. And finally, there is the canonical implementation of Muon, which is what you find in the modded nanoGPT architecture. So this speedrun is always changing as the record gets broken, and so different scalings are getting used. So initially, they were using the same scaling as what was used in the Kimi paper, but more recently, they've been using this alternative scaling, which is also different from what's in Scion. And so you have, it seems like, at least 3 choices. And it's not always clear which one is better, right? So I'm going to show you some experiments comparing these in a few slides. So let's look at the experiments next. The first one that I want to show you has to do with hyperparameter transfer. So in this context, we're training the nanoGPT architecture coming from the speedrun. With various widths, right? So different colored curves correspond to models of various widths. On the x-axis, we have like the learning rate, and on the y-axis, we have the validation loss. And so what we see in the top 2 plots is that for Atom and for Muon with the Kimi scaling, as we increase the model width, the optimal learning rate is actually shifting, right? It's getting smaller. And in contrast, as we scale the width with Scion or with unconstrained Scion, the optimal learning rate is actually fixed, right? They're all lying on a vertical line. And this is actually something that we can prove rigorously under some assumptions, the sort of assumptions you would find in the tensor programs series of papers, but nonetheless a proof. So you might ask, is the fact that Muon's not doing a hyperparameter transfer related to the scaling that Kimi is using? And this is not the case. So we reran the code with the new scaling, and you still see that the hyperparameters are not transferring, right? The step size is not transferring as we scale the width. So it's not a matter simply of just using the new scaling. It really has to do also with the fact that the typical implementation of Muon is using Atom on the vector parameters. And this is complicating things. So I talked earlier when I introduced the stochastic conditional gradient method about the constrained problem it would solve. And so we get basically a free bound for the stochastic conditional gradient algorithm on the norm of our parameters, because we're never going to leave the constraint set, just like in Frank-Wolf. For the unconstrained version of the algorithm, we also have a bound, but it's not fixed by the radius. It depends on the sum of the step sizes. And so Scion, the operator norm version of the algorithm, inherits these bounds. And we see this in practice. Here, we're training a convolutional neural network on CFAR10. And what we see is that the norms for Scion are fixed, right? They're not growing past a certain limit. Whereas in unconstrained Scion, they are growing for, let's say, the first 3,000 steps. And they're roughly growing like the square root of the number of steps. Okay, and it's only at around iteration 3,600 where we see the norm start to flatten out. And this is because we're using a stable decay learning rate. So we have a stable learning rate in the beginning with no warm-up, and this is where you see the norm growing. And then once the decay kicks in, the norm starts to flatten out. Okay, so if we had used a constant step size, it would have kept increasing. So following this, we tried to compare our algorithm to Atom and to Muon for training nanoGPT architectures, let's say. And so we did it with a 3 billion parameter model. And the idea of this experiment is that you want to see which optimizer can get below 2.9 validation loss the fastest, where fastest is measured either in the number of steps or the amount of wall clock time. And what we see is that first, all the spectral methods are beating Atom by quite a big margin. And then that unconstrained Scion and Scion are both performing better than Muon. And so this implementation of Muon is taken directly from the modded nanoGPT speedrun, but it was taken when we were writing the paper, which is back in November. So it's not the same code that's out there today, but it was the state of the art at the time when we ran the experiment. And I should also mention that Muon here, because it's the older version, it's using the Kimi scaling that was originally used in the speedrun as well. And for Scion and unconstrained Scion, we're using the sign on the first and the last layers. So we're using the sign spectral sign configuration for the norm. Another big difference between Scion and Muon, and also between Atom and spectral methods, is the sensitivity to the batch size. So what we see is that actually Atom is way more sensitive to the batch size than spectral methods. So in this experiment, we have some fixed token budget, and we look at what happens to the minimum validation loss as we increase the number of tokens in each batch. So when you have a fixed batch size and you start increasing, when you have a fixed token budget and you start increasing the batch size, you're going to do less steps, right? Less iterations. And this heavily impacts the validation loss of Atom. Muon, in contrast to Atom, is much less sensitive, but actually Scion and unconstrained Scion are even less sensitive than Muon. And this is not really a surprise, right? Because Muon, even though it is a spectral method, is using Atom on the vector parameters, right? So it's not a pure method in this sense. It's sort of a Frankenstein method that's mixing spectral methods and Atom. And so we see, at least in this context, that Frank Wolf is outperforming Frankenstein. Okay, moving on from language tasks, we can look at image tasks. So we trained an image transformer, something called a data efficient image transformer, coming from Meta or Facebook research. And so we're seeing that we're able to match the accuracy of Atom W with like much fewer number of epochs and also less wall clock time as well, even though that's not shown here. So the target accuracy here is something like 71 or 72%. And so in case you're wondering, like, is Atom well tuned in this experiment? This is also the results that are in the DIET repo itself. So we see that they have 72.2. We're comparing with something a little bit less. But for DIET base, we have 81.8. And we did the experiment also with DIET base, which has many more parameters. And we there are getting to 81.8% in much fewer epochs and also less wall clock time. And the wall clock time could actually be improved. So this is not the best you could do. Like some operations in our experiment could be parallelized better, and we could see an even bigger difference. So more important than just beating Atom, though, is the fact that in these experiments, we also see hyperparameter transfer. So this is a different domain. We're not looking anymore at text, but we still have the optimal learning rate that's transferring across these DIET models, as you see in the plot on the right, where the learning rate is on the x-axis and the test accuracy is on the y-axis. So it works also for training image transformers on ImageNet. We also did experiments with convolutional neural networks, looking at them on CFAR10 with a spectral sign. Maybe this is something I should have mentioned. We took the spectral configuration because we're looking at image data, right? So we're not using spectral sign anymore. We use spectral sign also for the convolutional setup. So here the notion of width is a bit different. It doesn't mean the same thing. When we scale the width, we're actually adding filters to our hidden layers. We're not making the filters bigger. This wouldn't really make sense. And we see that the step size is transferring. Here are some hyperparameter sweeps that are testing the relationship between the momentum and the learning rate. So you see the momentum on the x-axis and the learning rate on the y. And what we can see from this, so each column corresponds to a certain number of epochs of training. In the top row, you have unconstrained Scion. In the bottom row, you have Scion. And basically, if you're doing longer training runs in this experiment, it benefits you a lot to use a larger momentum. So typically, in the text experiments that I showed you, we were taking a momentum that was like 0.1. And here, we're taking a momentum that's much larger, closer to like 0.5. Okay, I want to finish with just some theoretical results. To talk about theoretical results, we have to make a few assumptions about our framework, our problem that we're going to solve. The main one is that we should have a Lipschitz smooth function. And so if I would have given this talk 5 years ago, I would have been in the audience saying, this is a very unrealistic assumption. You have like ReLU activations, which are non-smooth. You have max pooling, which is non-smooth. And this is true. But in the modern paradigm with transformer networks, we typically have continuously differentiable activations. And if we restrict ourselves to a compact set, like we do in Scion, then actually continuous differentiability is sufficient for Lipschitz smoothness. So we have this assumption automatically if the activations are continuously differentiable. The second assumption I'm going to make is that our stochastic oracle is unbiased and that it has bounded variance. This is also pretty questionable in the sense of realism, but it's a very common assumption in stochastic optimization, and we will also adopt it here. So with these assumptions, we get the following first preliminary convergence results. So for these results, we're going to take the step size to be dependent on the horizon, the number of iterations that we will run, but we will take the momentum to be independent of the horizon. And if you do this, then the type of convergence result you get is not convergence to a first-order critical point. Actually, what you get is convergence only to a noise-dominated region. So because the momentum doesn't go to zero and doesn't depend on the horizon, we can't kill this noise. So we get a noise-dominated region for the unconstrained version, for the gradient norm, and for the constrained version, if you're familiar with constrained optimization, the gradient norm is typically not going to zero, right? Even if we approach a critical point. So the correct notion for constrained optimization is not the dual norm of the gradient. It's rather something called the Frank-Wolf gap. So that's what you see in the expectation, this inner product. This is called the Frank-Wolf gap, and it's equal to zero if and only if we are at a first-order critical point, okay, for our constrained problem. So if we don't let the momentum go to zero, we don't get convergence really to a critical point. We get fast convergence, but only to a noise-dominated region. If we allow the momentum actually to go to zero, so if we have vanishing momentum, or if we allow it to be dependent on the horizon, there's somehow an equivalence here between vanishing and depending on the horizon, then we really get convergence to a first-order critical point in expectation, right? So the expected dual norm of the gradient is going to zero in unconstrained stochastic conditional gradient, and the Frank-Wolf gap is going to zero in the stochastic conditional gradient algorithm with these parameter choices. And something I really want to stress is that these parameter choices do not rely on any of the assumed parameters. So you don't see the Lipschitz constant appearing in these choices. You don't see sigma, the bound from the variance of our gradient estimator. These are really like the best you can do if you don't know this information. Okay, so several algorithms that you might already know are actually special cases of this stochastic conditional gradient framework if you take different choices of norms and momentum parameters. So if you pick your norm to just be the Euclidean norm, we saw already that the LMO in that case is just going to divide by the norm. And so in this setting, if we pick the Euclidean norm, we're going to get back normalized SGD. And if we take it with momentum that's not equal to 1, then we're going to get back exactly normalized SGD with momentum. On the other hand, if we pick like the L infinity norm, we saw that the LMO is going to be the sign, and in this case, we'll recover sign SGD and sign SGD with momentum, or sinum, as some people call it. And if we ignore what happens to the vector parameters, right, if we only consider what happens to the matrix parameters, then Muon is actually also a special case of Scion, where you take the operator norm or the spectral norm to be your norm for your layers. Okay, so actually we can unify the analysis of all these guys into one framework. And some selected related work that I would like to mention. First is the stochastic spectral descent. So this is an old paper in deep learning terms. It's 10 years old now. That was published by my co-author, Volkan Shaver, in 2015 in AI Stats, which was actually co-located that year with ICLR, where Adam was presented. So in the same conference where Adam was first presented, also spectral descent, this matrix sign algorithm, was also first presented. And now, 10 years later, we're finally coming back around and looking at these methods in more detail. Of course, it's related to the Frank-Wolf algorithm, as I already touched on, but also the stochastic Frank-Wolf algorithm. There's this nice paper by Makhtari and co-authors where they first used the momentum estimator with stochastic Frank-Wolf. There's this work on second-order optimizers called Shampoo, which is actually very related to spectral LMOs. If you disable the accumulation in Shampoo, then you get back the spectral LMO. And so in this sense, they're very related, even though if you literally write out the updates of Shampoo, it's like Adam, it's an update with respect to some Mahalanobis norm. So Euclidean in some sense. There's also the Muon blog post. So people ask me all the time, what's the difference between Scion and Muon? So the main differences are how they treat the scaling factors in the spectral LMO. The way that Muon is doing things doesn't lead to hyperparameter transfer, in contrast, let's say, to Scion. And there's also this difference in what they do for the vector parameters. So Scion is typically taking the vector sign for vector parameters, while Muon is doing Adam, which is not so different from the vector sign, but it does use this on-the-fly adaptation, right? So you have to keep track, for instance, of the second moment of these vector parameter gradients. There's also the Kimmy Moonlight paper. The difference, again, with our work is that they're using like this Muon with Adam, and they're also using a different scaling factor. And then also these preconditioned SGD works and some other works on the duality structure of gradient descent are also related to what we've done. So actually, most of these methods can be categorized together in this matrix that you see on the right. So in Scion, in the bottom right, we are doing the matrix sign on the matrix parameters. So this is why we're in the right column. We're not doing any kind of EMA or accumulating preconditioners like in Shampoo. And we're also doing the vector sign on the vector parameters. So this is why we're in the bottom row. We're not doing Adam on the bottom, on the vector parameters, which would put us in the top row. In contrast, Shampoo is doing accumulation on everything. Also, some variants of PSGD are doing something similar to this. And so this is why they're doing EMAs on both the vector sign and the matrix sign, while Muon is doing the vector sign with EMA, so this is Adam, but it's doing the matrix sign without EMA. It's not accumulating left and right preconditioners like in Shampoo. It's just computing the matrix sign at each iteration. So I think this is a good way to organize these methods and how they relate to one another. And if you're interested in reading the paper that spawned Scion, it's available on arXiv. It'll also be presented in like a week or so at ICML, where it was accepted. As I said before, if you want to give it a try, the GitHub link is there. We have also another paper extending this to L0, L1 smoothness using clipping that you can read if you're interested. But otherwise, I think maybe it's a good place to stop.